The way I think about what we are working on is, there is a great puzzle, which is why do laws of nature work at all? I mean, we know they're not true in the following sense. They teach you classical mechanics, and after a few years you get it. Then they suddenly teach you quantum mechanics. It looks nothing like classical mechanics. And then, they explain that there's a limit in which quantum mechanics goes into classical mechanics. So you have some picture that the world is an onion. There are layers of understanding, and first you get the outer layer, and then you go deeper and deeper. And I think this is too naive, but that's one of the religions that theoretical physicists have. That there are deeper layers of understanding, and you just have to dig deeper, and you will have quarks, and then there'll be something at Planck length, and stuff will happen. It's not, in accord with our human experience. I mean, human experience doesn't really work like that. And I think learning nonlinear dynamics helps you get a different point of view, which I think is broader. The way I think of things like classical mechanics and then quantum mechanics is that if there are symmetries in a world, or very good symmetries in a world, broken very weakly, etc., then there is something called Noether's theorem. Emmy Noether is one of the amazing 20th century mathematicians. So she did a little bit of physics, she did many other things, but the Noether theorem says that if things don't change in time, there should be something conserved, and that thing that's conserved is conservation of energy. Now, when you actually really dig in Noether's theorem, because it doesn't agree with your experience of the world. I mean, you get to be 78 and you get to be less energetic and things go down. It's not just our experience. And it turns out that if you have a variational principle, and that's a big if you can derive your law of nature from having some function that you evaluate on a fictitious trajectory and vary, and if it's zero, then it's a classical equation of motion or quantum mechanics, and you have a symmetry, then you have Noether's theorem. So it's not true. The things, it's very often you don't have a symmetry, and it's a perfectly good description of the world. So, for example, when you are pondering what the brains do, you have a fairly good understanding of the basic elements. So there are neurons, we understand them in various level of depth and detail for 2 centuries roughly, at least 150 years. They're the basic blocks, the little machinery, there are lots of them. Each one of them you could record its state, its action potential technically. So that is a neuron 1, neuron 2, neuron 3. I'm going to write Cartesian coordinates in a weird way, because then the other ones are somehow outside of this room, they're pointing in different directions. There is neuron 4, and there is a neuron, I've forgotten the real number, but let's say neuron 10 to the 7th. There are lots of them, right? And still, I can do stuff. There are lots of them, and how does this happen? So the picture I'll try to explain in a very simplest way today, and that's not how Strogatz writes it up, but that's why we are thinking about this, is to say, actually, there is some function that's like energy or potential or something like that. where these coordinates are the floor. So, you can imagine there is some kind of plane, and let's see, is this a color or orange? There's a landscape. It's a beautiful landscape. It has mountains as far as I can see. Some are high, some are low. And then it has green valleys. If I happen to be down in a valley, my life is very constrained. I'm either at the bottom of the valley and it's very tedious to get up, so I just sit in my house, or there is some stream or something. There is few degrees of freedom, technically. And I do my thing. I turn my head this way, I turn my head that way. That's a very simple motion which is described by this thing. So there is something very simple in here. And when it's really, really boring, I'm at the bottom and nothing happens. So that part is not covered in a course. That would be a zero-dimensional world. But the first thing that can happen is, I can actually wander in some place in the valley, and I wander on this line. And it has ends, I can go here and there. And that's what the first part of this course is about. It says that even though the world that we live in is incredibly rich and complicated, every so often we have to do a task. Task can be similar, simple. And then purpose of this geometrical way of thinking that comes from Poincaré and that we teach you in this course is to find qualitatively what can happen. And then if I have to do something else, I'll have to climb, jump, get kicked around, and do something else. That's what happens in, let's say, biological world. That's what we are doing in this course. It turns out it's quite useful to understand in detail things that are only in one dimension to start with, and then 2, 3, and so on. So for a while, we'll say there isn't much we can do. So all we can do is, let's say, my action potential, not the coordinate on the floor, but the physical property or biological property of the system, which we call here x. This is the world. I'm an ant, and I can only move in this one-dimensional world. Or I'm a duck. There are other ducks. And here we are. I don't feel like drawing ducks very much. And for starters, let's just describe what can happen when I have a world filled with ducks. Every duck, this is our state space. So every duck at a particular place in this world, and at a particular time, that's a point in the state space. We have been indoctrinated into believing that the world is described by differential equations. You don't question it. And you can put it on a computer, we'll do it, and you can solve them. So obviously it's true. And I just want you to think of one thing. Look up in the clouds and ask yourself, is there a supercomputer in the sky that goes chugga, 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 chugga? Because we know the equation, the Navier-Stokes plus humidity plus temperature plus this. We know the equations. We can put them on computer. It costs enormous amount of money and time to put them on computer. It's very expensive to solve them, both in human and consumption, energy consumption term. The nature just solves them effortlessly. So, I'm teaching you differential equation course. Don't for a moment believe that nature solves differential equations. Really think what it does. So it does something else. So now there is a full errand in all of science. Well, physicists are very susceptible to it. And it's essentially a religious attitude. The full errands is to say, I'm a scientist, I can enumerate everything that can happen, and that's it. I'll give you fundamental equation of the nature, and from it everything will follow. The word at the beginning. And I'll do that. Now, in one dimension we can do it. So, there are examples where we actually can explain everything. We'll very quickly leave this territory, but here we can actually enumerate all possible things and describe them in lots of detail. And it turns out that in the real world, nobody lives on a line. The activity of a neuron cannot go from millivolts to teravolts or whatever. That doesn't happen. But this idea of understanding segments that look linear will work also on little curvy linear things, and it'll be not a bad idea. And if you're an engineer or economist or somebody else, you might have a different word for it. And they have a property that nothing happens. So they're kind of, you would think, outside of the scope of our course, because we're interested in dynamics, we're interested in change. But these are guys that are not changing, so they're not interested. It turns out that whatever you do to understand its dynamics, you always first have to find equilibria. Are they there? What they are? It turns out that they'll be like the mountain peaks in the landscape I told you, and they're very important. Nothing happens, but they separate regions of qualitatively different behavior. So nothing is more important than first figuring out what the equilibria of a system are, or fixed points. So that's the main message of this course. We'll do it in 1, 2, 3 dimensions. We always find them first, and then we'll try to piece the world from them. Then, if I'm someplace and my velocity is positive, I'm on a highway, I'll be increasing the distance along the positive direction. So I know that I will be moving this way whenever I'm positive. And if my distance is negative, then I'll try to go back. Then maybe this curve will go like this. And that's about all that can happen for ducks on the line. They're either imprisoned between two fixed points, so if I'm on a fixed point, that's it, I'm done. I will be forever there. I have tenure and I don't change from now on. Here I'm locked, or I run away. So the fool's errand of finding all possible kinds of things that can happen in the world, in one-dimensional world works. I'm either not doing anything, or I'm gliding on an interval, or I'm marching off to infinity, or I've come from infinity. So that's it, the three possible things. But we can get more information than that. We might be interested in how fast this is happening. Is it going to take a millennium, or it'll take a week, or what's the rate of change? And the next thing that you will do for any system, no matter how complicated. So now I'm on a line, but you know, if there was a mountain and you were someplace on that mountain, I will ask you to make a little chart of your neighborhood, and there'll be a piece of paper, flat, because in a smooth landscape like we are on a sphere, but Atlanta looks flat for us, you will make a linear chart. And it turns out describing what happens on a linear chart is very easy, and we'll just do it in higher dimensions, but in this case it's extremely simple. So the next piece of information we can get rather cheaply from a dynamical system is what happens in a neighborhood of an equilibrium. Generically, you know, you can always do that. This will give me exponential in this neighborhood, which will be okay for some region in which I have a criterion that says I can neglect, this is a sine of x, and I can write as x plus third factorial x cubed, and I can expand this thing as a Taylor series, and as long as this is smaller than that, it's a good approximation. So there will be some region in which linear way of thinking is useful. It might look kind of silly to you, but if you want to learn general relativity, if you want to learn any differential geometry, that's what you do. You do not know how to describe a general nonlinear landscape, but you know how to put little charts and put them together. You know how to get from here to California using maps of states, even though none of them are really flat, they're pretty good accuracy flat. So that's much more powerful than it seems. And in one dimension, this linear law is really easy to describe.